So now we're going to try to backtrack a little bit and talk about something called combustion analysis. Now, this may seem just much like we are backtracking, but in reality, you needed to know some skills in order to get here. So this is very similar to elemental analysis, but what we're doing here is we're taking a sample of a hydrocarbon. So a hydrocarbon is something that's composed of carbon and hydrogen only. And what we do is we burn this in the presence of O2 gas. So that's going to produce CO2 and H2O, just like we talked about with combustion problems. So we can determine the amount of carbon and hydrogen you have in your original sample and then determine the empirical formula. So to give that to you in a more graphical context, when you complete this reaction, you will figure out what both A and B are, because otherwise you don't know. You don't need to have a balanced equation here. You just are trying to figure out what A and B are. So here's an example type of problem. So let's say we sent 3.13 grams of a hydrocarbon sample in for combustion analysis, and your sample comes back with 10.4 grams of CO2 and 2.66 grams of H2O. So there's a hidden thing here that I first want to point out. It doesn't matter how much your sample was. It really doesn't, because we're looking for molar ratios and we don't even need to really keep that into account. So that's why I wrote this little note to the side. But what we actually need to do is we need to convert the grams of CO2 into moles of CO2, which will give us then the moles of carbon, because we can figure out what the relationship is. And then we do the same thing to H2O. We convert those grams into moles of H2O, but we gotta be careful here when we go into moles of hydrogen. And then just like we did in elemental analysis before, we're gonna determine what our ratio is between carbon and hydrogen by dividing by the lowest number of moles. So to start that process, I need to know what the molar mass is for both CO2 and H2O. And so once we have that, we're good to go. So we start by saying we have 10.4 grams of CO2, convert that to moles of CO2 through the molar mass, and then we convert that to moles of carbon, because that's what we're actually after, not CO2, and we do that through the relationship, because every one CO2 has 1 mole of carbon, and so we figure out how many moles of carbon we have that way. Then we're going to do something similar with H2O. We take the amount of grams we have there, convert that into moles of H2O, but you got to be careful in the next step, because for every mole of H2O, you have 2 moles of hydrogen. So make sure that that is something you take into account. And so you have the moles there. Then, just like we did before in elemental analysis, you divide by the lower number between those 2 moles. And in this case, that is moles of carbon. So 0.236 moles goes on bottom of 0.295 moles of hydrogen. And we get that there's a ratio of 1.25 moles of hydrogen for every mole of carbon. Remember, atoms, we need to make sure that they're in whole number ratios. So given that I have 1.25, that tells me I need to multiply by 4 to get those into whole number values, and that's how I end up with C4H5. Just to remind you, that was another way to say we had C1H1.25. So multiply the 1 by 4, and that's how we get the 4, and multiply the 1.25 by 4, and that's how we get the 5. You need to multiply by whatever amount you need to in order to get whole number ratios. Thank you very much. Good job.